Welcome back, everyone. I am absolutely thrilled to have you here for today's explainer, where we're setting the stage for a really intense chemistry matchup. Today, we're diving into the fundamental forces of coming together and breaking apart. We're going to break down exactly how combination and decomposition reactions actually operate. But more importantly, we'll look at how you can completely master them for your exams by recognizing their perfectly mirrored structures.
All right, let's jump right into Section 1, the classic exam question. So, picture this. You're sitting there, staring at a blank exam paper, and you get hit with this classic CBSE question. Why are decomposition reactions called the opposite of combination reactions? Write one equation each. Now, it sounds incredibly simple, doesn't it? But here's the thing. Examiners aren't just looking for a simple yes or no. They want to see the mechanics. They want you to prove this fundamental opposition using specific reaction examples. So let's build that proof together, step by step.
To start, let's look at the basic blueprint before we even touch the real chemicals. On one side, we've got our combination framework. A plus B yields AB. It's just two distinct entities merging into one. Now, mathematically reflect that on the other side for our decomposition framework. AB yields A plus B. Whatever was formed in the first equation is literally torn apart in the second. Keeping this kind of visual symmetry in your head is going to make the actual chemistry an absolute breeze.
Moving right along to Section 2, combination. Two become one. A combination reaction is beautifully straightforward. It's quite simply when two things become one. You start with multiple separate elements or compounds, and through the magic of a chemical reaction, they bond together to form a single, unified product. Now, here is where our main focus really matters today, the specific reaction examples. Take a look at this one. We have CaO added to H2O. Those are our two separate starting ingredients, and together, they yield our single product, CaOH2. So calcium oxide reacting with water perfectly demonstrates our two become one rule. This is your golden combination equation for the exam. You definitely want to lock this specific reaction example into your memory because we're going to use it to a huge advantage in just a second.
Which brings us to Section 3, decomposition, the breakup.
As you might guess, this definition completely mirrors the previous one. A decomposition reaction is basically when one complex thing splits apart and becomes two separate products. You're starting with a single, complex compound, and the reaction fractures it. The bond is officially broken.
Let's examine the reaction example for this chemical breakup. We start with just one thing, CaCO3, which is calcium carbonate. Apply some heat, which is often represented by that delta symbol, that little triangle above the arrow, and it yields CaO plus CO2, calcium oxide and carbon dioxide. Our single compound just fractured into two distinct pieces. For your exams, this is the absolutely essential decomposition equation you need to be able to write down.
Let's move on to Section 4, the CaO memory trick.
Okay, if you compare the two reaction examples we just learned side by side, a massive visual overlap suddenly appears. Memorizing two completely different chemical equations can feel a bit overwhelming, I know, but do you see what they share here? CaO appears in both reaction examples. In the combination reaction, calcium oxide is one of the starting ingredients, but in the decomposition reaction, it's one of the final products. Guys, this is the absolute perfect exam trick. By anchoring your memory to just that one specific compound, CaO, you can easily reconstruct both equations to prove to the examiner exactly why these two reaction types are reverse processes.
Now, let's dig a little deeper in Section 5, the energy shift.
To really ace this topic, we need to look under the hood at the invisible forces driving these opposing reactions. It's not just about atoms shuffling around, it's about how energy behaves in these opposite scenarios. Combination reactions are mostly exothermic because forming new bonds actually releases energy outward. Conversely, decomposition reactions are mostly endothermic. To force a molecule to break apart, to literally snap those chemical bonds, the reaction has to absorb energy from its surroundings. This is often in the form of heat, just like that delta symbol we talked about a minute ago. So they aren't just opposites in structure, they are exact opposites in how they handle energy too. One releases it while the other demands it.
And finally, Section 6, what happens next?
So we've successfully answered the classic exam question, we've defined the structural opposites, and we've nailed down those reaction examples using our handy CaO trick. But, the world of chemical reactions doesn't just stop at coming together and breaking apart. Which leaves us with this final, honestly rather aggressive question to ponder. We know what happens when things combine and when they decompose. But what happens when one element forcibly kicks out another element from its compound? This points to a much more competitive type of chemical interaction known as a displacement reaction. So how do we visually map out that kind of chemical takeover? Well, you'll just have to keep your curiosity burning for our next explainer. Until then, keep analyzing those structures and happy learning.